Bismillahirrahmanirrahim. Assalamu alaikum dear students. We are going to start today the lecture 18 of Discrete Structures CSC 102. In the previous lecture we have discussed the transitive closure of relations, combining relations, and we have discussed also the equivalence relations. What is equivalence relation? I repeat here, a relation which is reflexive, symmetric and transitive is called an equivalence relation. We have also started equivalence classes, and we have constructed some equivalence classes of sets. So today we are going to continue the last topic, equivalence classes, and we shall discuss some properties of relations, properties of equivalence classes, and then we shall discuss equivalence classes of congruence modulo 3, equivalence classes of congruence modulo n and their properties, and at the end we shall discuss modular arithmetic, partial order relations and Hayes diagrams. So in the last lecture we have defined that an equivalence relation is a relation on a set which is reflexive, symmetric and transitive. So now we are going to discuss some properties of the equivalence relation. In the previous lecture we have seen that if we have a set A, R is an equivalence relation on A, and we have computed equivalence classes. Now if we have two equivalence classes for any two elements A and B, if these two elements A and B are related to each other under the relation R, if A is related to B, then the equivalence class of A must be equal to the equivalence class of B, as we have studied in the previous lecture. And when we have computed the equivalence classes, you have seen that we have equal classes for some elements. Actually, any two elements of A which are related to each other under the relation R, then their classes must be same. So here we shall prove it, whether that two equivalence classes are equal if A is related to B or not. So let A be a set and R be an equivalence relation on A. R will be reflexive, symmetric and transitive, and suppose A and B are elements of A such that A is related to B. So we suppose it, and we are going to prove this is equal to this. Now as you know that equivalence classes are actually sets, so to prove that two sets are equal, how we proceed? We will show that A is subset of B and B is subset of A. This implies A is equal to B. So this is what we have to prove to be two sets, for two sets to be equal. So now we are going to prove that this equivalence class A is subset of equivalence class of B, and then we shall prove equivalence class of B is subset of equivalence class A. So let now how we prove any set A is subset of B. We take any arbitrary element of A and we prove that that element belongs to B. Then we have discussed it earlier in the when we have discussed sets. So to prove this A is subset of equivalence class A is subset of equivalence class of B, we take some element X of the equivalence class A, and then we shall prove that X is also the element of B. Since X is element of A, then X is related to A by the definition of equivalence class, because in equivalence class all those elements of A are belongs to that equivalence class if X is related to A by definition of equivalence class. But we have supposed that we are given that A is related to B, then A is related to B. Now R is a relation which is also the transitive relation. This means that by the transitivity of the relation X is related to B, because we say that X is related to A and A is related to B. What does it mean? X is related to B by the transitivity of this relation. It means X belongs to B because X is related to B. If X is related to B, it means X belongs to the equivalence class of B. So therefore we conclude that this equivalence class is a subset of equivalence class of B. Now we have to prove the reverse, that we have to prove B equivalence class of B is subset of equivalence class of A. Now prove that B is subset of A. We shall prove it on the same lines. We choose some arbitrary element of B and then we shall prove that X belongs to the equivalence class of A. Now if X belongs to B equivalence class, then X is related to B, and by definition here we have supposed that A is related to B, and then A is related to B by the hypothesis. Since R is symmetric, as R is an equivalence relation, R is symmetric, then we can write B is also related to A. That is, B is related to A. Now if X is related to B and B is related to A, what does it mean? X is related to A. Why? Because R is transitive relation. So therefore if X is related to A, this means X belongs to the equivalence class of A. Therefore we can say that equivalence class of B is subset of equivalence class of A. We have proved that equivalence class of A is subset of equivalence class of B, and equivalence class of B is subset of equivalence class of A. It follows that equivalence class of A is equal to equivalence class of B by the definition of set equality. So we have concluded that if A is related to B under the same relation R, then the equivalence class of A is equal to equivalence class of B. Another property of the equivalence classes is basically if A is a set, R is an equivalence relation on A and B are any two elements of A, then either equivalence class of A intersection equivalence class of B is empty, means they don't have any common element, or they are equivalent. So this theorem is somewhat like the previous theorem. Now in the previous theorem we had if A is related to B, but here we don't have A is related to B. So in a relation R, there are two possibilities: either A is related to B or A is not related to B. If A is related to B, then we have the previous theorem that if A is related to B, then the equivalence class of A is equal to the equivalence class of B. So this is the previous theorem. Now here, if A is not related to B, then equivalence class of A and equivalence class of B, they both don't have any common elements, or we can say that intersection of these two classes must be empty. So how to prove this theorem? The statement of the theorem has the form this: if P then Q or R. This, if we write it in the logical form, then we can write it as if P then Q or R, where P is the statement, A is the set, R is an equivalence relation on A, and A, B are elements of A. This is what the P statement. Until here, from here until here we have this statement. Now what is Q? Q is intersection of these two classes empty. R is the statement these two classes are equal. So as we have studied in logic, to prove this theorem we shall prove the logical equivalent statement. This statement is logically equivalent to this statement. If P and not Q, then R. So we suppose that P is true, Q is false, then we shall prove R. That is, we will prove that if A is a set, R is an equivalence relation on A, B are elements of A, and this is not empty, then this. So how to prove this? Suppose A is a set, R is an equivalence relation, A and B are any two elements of A, and A intersection B equivalence classes of A intersection equivalence class of B is not empty. Basically here we have the negation of Q. So if equivalence class of A intersection equivalence class of B is not empty, then there must exist some element X in A which belongs to both of these equivalence classes. That is, X belongs to intersection of equivalence class of A and equivalence class of B. Now, by the definition of intersection, X belongs to this, X belongs to this, both classes. If X belongs to A, then X is related to A, and if X belongs to this B equivalence class of B, then X is related to B. By the definition of equivalence class, since R is symmetric, because R is an equivalence relation, so if X is related to A, then A is related to X, because R is symmetric. R is also a transitive relation because R is an equivalence relation. So A is related to X and X is related to B. By the transitivity, we can say A is related to B. Now, if A is related to B, by using the previous theorem, we can say that equivalence class of A is equal to the equivalence class of B, or we can prove it as we have proved in the previous theorem. So we have concluded that if R is an equivalence relation defined on a set A and AB any two elements of A, then either their equivalence classes are distinct, means they don't have any common element, or their intersection is empty, or they are equal. So there are two possibilities. Now we are going to define equivalence classes of congruence modulo 3. Let R be the relation of congruence modulo 3 on the set Z of all integers. That is, you know already what is the congruence modulo 3 relation. We have discussed it in the previous lectures. So under this relation, any two elements M and N of Z, M and N, these two elements basically belongs to Z. Z is the set of integers, you know. So M is related to N if and only if 3 divides M minus N. So this is basically the relation of congruence modulo 3. Then we write it, M is congruent to N mod 3 or N modulo 3. So we have to compute the distinct equivalence classes of R, and we have to show that whether this relation is an equivalence relation or not. How we shall prove whether this relation is equivalence relation or not? First we have to prove whether this relation is reflexive or not. As we have to prove M is related to M. What does it mean? 3 divides M minus M, as this is equal to 0, so the 3 divides 0. Any number divides 0, therefore M is related to M, therefore this relation is reflexive. Now we want to prove that whether this relation is symmetric or not. So to prove that this relation is symmetric, we have to prove if M is related to N, this implies N is related to M. So if M is related to N, what does it mean? 3 divides M minus N, and we have to prove 3 divides N minus M. So this easily we can see that if 3 divides M minus N, then by interchanging the signs, minus M minus N, M, so 3 divides it also. Therefore this relation is symmetric. Similarly, we can prove that this congruence modulo 3 relation is an equivalence relation or a transitive relation and then equivalence relation. So now we are going to compute the equivalence classes. So if we have any integer a which belongs to z, then equivalence class of a contains all those integers, means all those elements of z which are related to this a. If x is related to a, this means 3 divides x minus a. What does it mean? X minus a is multiple of 3, or we can say that x is equal to, we can say that x is equal to a plus 3k. Now the equivalence class of a basically contains all those integers which are basically multiples of 3 plus a. So if we choose a to be 0, in particular if we choose the first element of z0, then this 0 basically contains all those elements which are multiple of 3k plus 0. Now for some integer k may be an integer, so x is equal to 3k. Now if we take k to be integer 0, then x is 0. This 0 is the first element, and then k1 is 3. If we take k2, we get 6. If we get k3, 9, and so on. If we take k minus 1, we get minus 3. If we take k minus 2, we get minus 6. If we take k minus 3, we get minus 9. So here we choose also the k to be an integer, which is 0 plus minus 1 plus minus 2 plus minus 3 and so on. So by using this this relation, we can find equivalence classes of all the integers 0, 1, 2 and so on. So now equivalence class of 1, this is basically all those x which satisfy this relation. Now if we choose k to be 0, we get 1. If we choose k to be plus 1, this is 3 plus 1, 4. If we choose k2, then this is 3 2 is 6 plus 1, 7 and 10 and so on. If we choose k minus 1, we get minus 3 plus 1, this is minus 2. If we choose k is equal to minus 2, then we get minus 6 plus 1, minus 5, and then this. In short, we write the integer for which we have to calculate the equivalence class in the center, and then we add up 3 on the right hand side and we subtract 3 on the left hand side in each successive terms. So here we have 3 plus 0 plus 3 plus 3 plus 3. So 0 plus 3, 3, 3 plus 3, 6, 3, 6 plus 3, 9 and so on. The next term will be 12 and then 15 and so on. Here we get minus 9 and minus 12 and minus 15 and so on. So we write the integer for which we have to calculate the equivalence class, and then we add up 3 on the right hand side and we subtract 3 on the right hand side to get the successive terms. Similarly, here you can see to calculate the equivalence class of 1, we write in the middle 1 and then we add up 3 on the right hand side, again 3, again 3, again 3. The next term will be 13 and then 16 and so on. On the left hand side, to get the next term, we subtract 3. 1 minus 3 is minus 2, minus 3 minus 2 minus 3 is minus 5, and minus 5 minus 3 is minus 8, and minus 11 minus 14 and so on. Similarly, we can immediately write the equivalence class of 2. We write 2 in the middle, we add 3 in each term to get the successive term. We subtract 3 in each term to get the successive terms. So this is all. And for 3, how we can calculate the equivalence class of 3? Since 3 is related to 0, as we have 3 and 0 are both in the same class, or 3, we can check here, 3 is related to 0 because 3 is related to 0 because 3 divides 3 minus 0. 3 divides 3 minus 0, so 3 and 0 are related. Therefore, the equivalence class of 3 and 0 must be same by using the previous theorem as we have discussed here. If A is related to B, then equivalence class of A must be equal to equivalence class of B. So here in this example, example of congruence modulo 3 is related to 0. Therefore, equivalence class of 3 must be equal to equivalence class of 0. Similarly, equivalence class of 3 is equal to equivalence class of minus 3 and 6 and minus 6, because all these integers are related under the relation R, congruence modulo 3. If all these integers are related, then their equivalence classes must be same. If we want to calculate the equivalence class of 3, for example, in the same manner as we have calculated for 0, 1, 2, 3, 0, 1, 2, then how we calculate? We write 3 in the middle, and then we add up 3 on the right hand side, 6, 9, 12, and so on. And on the left hand side, we subtract 0. Also, we subtract 3. 3 minus 3 is 0. 0 minus 3 is minus 3. Minus 3 minus 3 is minus 6, and so on. This class is exactly same class as this class. These two classes contains the exactly same elements. So therefore, we conclude that 0 equivalence class is equal to the 3 equivalence class. Similarly, we can check for minus 3, for 6, 9, 12, and so on. So all these elements are related to each other. If all these elements are related to each other, then their equivalence classes must be same. So therefore, we conclude that 0 equivalence class of 0 is equal to equivalence class of 3. Similarly, equivalence class of 3 is equal to equivalence class of minus 3, 6, minus 6, 9, minus 9, 12, minus 12, and so on. Similarly, equivalence class of 1 must be equal to the equivalence class of 4, because 1 and 4 are in the same equivalence class. If they are in same equivalence class, then they must be related. If they are related, then their equivalence class must be same. So all these elements which are in this class, they are related to each other. If they are related to each other, then their equivalence classes must be same. So 1, 4, minus 2, 7, minus 5, 10, minus 8, and so forth. Equivalence classes of all these integers must be same. Similarly, for 2 is related to 5, 2 is related to minus 1. So equivalence class of 2 must be equal to equivalence class of 5, and equivalence class of 5 must be equal to equivalence class of minus 1. And 8, 11, minus 4, minus 7, all equivalence class of all these integers must be same. So what we concluded here, that we get only three equivalence classes, three equivalence classes which are distinct, which are different from each other. So either these three classes are distinct, means their intersection is empty, and all other equivalence classes are same as the equivalence class of 0, 1, or 2 if they satisfy that if they are related to one of these three integers 0, 1, 2, 3. So we get only three equivalence classes. The first class is the equivalence class of 0, the second is the equivalence class of 1, the third is the equivalence class of 2. It contains all these elements, it contains all these elements, it contains all these elements. So 0, 1, 2 are the only distinct classes. Now we check another interesting thing in these equivalence classes, that these three classes cover all the integers. You can check here, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Here we have 12, 13, 14 and so on. Here we have 0, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8, minus 9, minus 10, minus 11, minus 12 and so on. So these three classes basically divides Z, the set Z of integers, into three subsets which are distinct. So if we take up the union of these three classes, we get again the set of Z integers, and the intersection of these three classes is empty. If we take intersection of any two classes, there is not a single element which is common in any two of these equivalence classes. So equivalence classes of congruence modulo 3 basically they have divided Z into a partition. They have divided Z into three subsets, which is basically a partition of Z according to the definition of partition which we have discussed in the previous lecture. These three classes, these three sets are basically they form a partition of Z, set of integers, and as their union is Z and intersection of any two classes is empty. So the congruence modulo 3 relation have divided Z, or have partitioned the set Z of integers. So we conclude here that if we have an equivalence relation defined on a set, so equivalence relation on any set divides the set into a partition, means divides the set into subsets, number of subsets, which basically forms the partition of that set, as we have seen in this case of the set of Z of integers. So here we have considered a particular case of congruence modulo relation. Now we are going to define the equivalence classes of congruence modulo n relation. So this is basically a more general case than the congruence modulo 3 relation. So here whatever we take the modulo 2, 3, 4, 5, anything, basically this relation divides also the set Z into a partition, or basically we can say that this relation partitions the Z set of the set Z of integers. Congruence modulo n is an equivalence relation. We will show it. We can show it easily. So if where n is any integer which is greater than or equal to 1, not equal to 1, congruence modulo n is an equivalence relation on the set of all integers. The distinct equivalence classes of this relation basically, as in the congruence modulo 3 relation, how many classes we got? These are basically 0, 1 and 2. So 2 is basically 3 minus 1. If we choose n to be 3, we get the same things as we have discussed for the congruence modulo 3 relation. So if we take the congruence modulo n relation, how many equivalence classes we shall get? It is from 0 to n minus 1, and all these classes must be distinct and they must define the partitions of the Z. So how we define these classes? The congruence class of any integer a, where a is from 0, 1, 2 and so on, is basically all those integers of z such that m is congruent to a mod n. That is, a must be related to m. Or equivalently, we can say that equivalence class of A contains all those m which we can write in this form as we have written in the case of congruence modulo n relation, congruence modulo 3 relation. So first we have to prove that the congruence modulo n relation is an equivalence relation. So we have to prove that this relation is reflexive, symmetric and transitive. Suppose A is an integer. To show that A is congruent to A mod n, we must show that n divides A minus A, but A minus A is 0 and any number divides 0. So therefore A is congruent to A mod n. Therefore we can say that this relation congruence modulo n is a reflexive relation. Now we have to prove that this relation is symmetric. Suppose A and B are any integers and A is related to B. A is related to B means A is congruent to B mod n. Then we must show that B is congruent to A mod n. But since A is congruent to B mod n, then n divides A minus B. Thus, by definition of divisibility, A minus B is equal to nk. We have already studied the divisibility, in which we have studied that we can write this as this. If n divides some integer, then we can write that integer as a multiple of n. So if we multiply both sides by -1, then we get here b minus a. So here instead of minus nk, we can write n minus k. Here n is some integer. The k is some integer. Then minus k is also an integer. So b minus a is equal to n into minus k. We can write it as, this means that n divides b minus a. If n divides b minus a, then b is congruent to a mod n. Therefore b is related to a. Here we have supposed that a is related to b. So we have proved that b is related to a. Therefore this congruence modulo n relation is symmetric. Similarly, we can prove that this congruence modulo n relation is transitive. For that, we have supposed that A is related to B and B is related to C. We have to prove that A is related to C. So we suppose that A is related to B and B is related to C. It means A is congruent to B mod n. B is related to C. B is congruent to C mod n. We must show that this. Now we have to prove that this congruence modulo n relation is transitive. To prove it transitive, we suppose that A is related to B and B is related to C. Then we have to prove A is related to C. So if we suppose this, what does it mean? It means A is congruent to B mod n, B is congruent to C mod n, and we have to prove this, which is A is congruent to C mod n. So if A is congruent to B mod n, then n divides A minus B, and B is congruent to C mod n means n divides B minus C. So as we know that if m divides k and m divides p, then m divides k plus p. So you should check the properties of the divisibility. In that we have seen this, that if m divides k and m divides p, then m divides k plus p. So what does it mean? If n divides a minus b and n divides b minus c, then n divides the sum of both a minus b and b minus c. So we can cancel up this. This is equal to a minus c. What does it mean? N divides a minus c. Therefore A is congruent to C mod n. Therefore this relation is transitive, and we can say that equivalence, the congruence modulo n relation is reflexive, symmetric and transitive. Therefore this relation is an equivalence relation. Now some properties of the congruence modulo n relation. Let a, b and n be any integer, and suppose n is greater than 1. The following statements are all equivalent. N divides a minus b, a is congruent to b mod n, a is equal to b plus kn, a and b have same remainder when divided by n, and the last is a mod n is equal to b mod n. We have already discussed these functions. A mod n, what is a mod n? This is basically remainder when we divide a by n. So we can prove these properties, but for I omit the proof of these properties. For proofs you can consult the book of Discrete Mathematics written by Susanna. So the next theorem is this, the modular arithmetic. In this topic we shall discuss some arithmetic of this congruence modulo n relations. Arithmetic means how we can add, how we can multiply, how we can perform such type of operations in the congruence modulo n relations. So let a, b, c and d and n be integers with n greater than 1, and suppose a is congruent to c mod n and b is congruent to d mod n. Then the first property is that if we add up this and this and this, we can add up a, b, c, d. Even then n divides the difference of c plus d and a minus a plus b. So if a is congruent to c mod n, b is congruent to d mod n, then this property holds with a plus, and this property holds also with the minus. And in this property we can multiply first and second. This is what it is here, given here. Even then n divides this, ab is congruent to c d mod n. The fourth property tells us that we can multiply on both sides. That is, if a is congruent to c mod n, then we can multiply a by m and c also by m. Even then this congruence will be true. So we can multiply by m on both sides. You can say it on the congruence modular relation. So we are going to discuss only the proof of the third part. I left the other parts as an exercise for you. You can do it easily, the third part. So now we have to prove AB is congruent to CD mod n. Suppose A, B, C, D and n are integers with n greater than 1, and suppose A is congruent to C mod n and B is congruent to D mod n. This is basically the hypothesis of the theorem. If A is congruent to C mod n and B is congruent to D mod n, then there exists integers s and t such that A is equal to this and B is equal to this by using this property. So we can write it as we have written in the congruence model 3 relations. So if A is C plus Sn and B is D plus Tn, so S and T are some integers, we multiply both these, A into B, this is equal to C plus Sn into D plus Tn. We perform the usual multiplication here and we take here n as a common, we can take it. Now here we get ct plus sd plus st. Here n, we have n square, so we have 1 n here. Now what is s? Integer. What is t? Integer. What is c? Integer. What is d? Integer. So all of these numbers are integers, and while studying sets we have proved that while studying proofs and set theory, number theory, we have studied that product of any two integer is a integer, sum of two integer is an integer. So we can say that this whole term is an integer because c is integer, t is integer, s is integer, d is integer, s, t, n are all integers. If we multiply integers and then take the sum of integers, we get an integer. So we can say this is some integer k. So we can write ab is equal to cd plus n into some integer k. So what does it mean? It means a basically this means that n divides a b minus cd. If n divides a b minus cd, then what does it mean? It means a b is congruent to c mod n. This is what we have to prove here. So similarly we can prove the other properties which are given here in this theorem by using a simple logic. So now we are going to verify the following statements, that whether this is true or not, what we have defined. Now here 55 is congruent to 3 mod 4, and 26 is congruent to 2 mod 4. Now this is true, this is true, because 55 minus 3 is 52 and 4 divides 52, and 26 minus 2 is 24 and 4 divides 24. So these two are true. Now we are going to prove 55 plus 26 is congruent to 3 plus 2 mod 4. This is true, you can see it here. Similarly the minus property, similarly the product property, similarly the square property. The another property which I have missed here, basically this property is not into m, this is basically written here. There is a mistake here. This fourth property is basically a power m is congruent to c power m mod n. So sorry for this, there is a mistake here. If we have a is congruent to c mod n, then any power of a m, same, we can take power on both sides. If a is congruent to c mod n, then am is congruent to c power m mod n. So this is the actual property which is I should define here. So here is a mistake. So in this here we are going to prove that 55 power 2 and 3 power 2, basically these two are also congruent. So first, as you can see here, that 55 plus 26 is equal to 81 and 3 plus 2 is 5. Now by definition of congruence model n, to show that this 81 is congruent to 5 mod n, then 81 4 must divides 81 minus 5. So 81 minus 5 is 76 and 4 divides 76. This is true. Similarly, you can check the second, third and fourth. So this is what these are the modular the properties of modular arithmetic. So now we are going to discuss the partial order relations. What is a partial order relation? By definition, as we have discussed in the previous slides, equivalence relation. An equivalence relation is basically that relation which is reflexive, symmetric and transitive. Now partial order relations, a relation R on a set A is said to be partial order relation if and only if R is reflexive, R is antisymmetric and R is transitive. So here we have changed only one condition here, the symmetric. In equivalence relation we have symmetric, in the partial order relation we have the antisymmetric. The relation R must be antisymmetric. Antisymmetric, you know that a relation R is antisymmetric if A is related to B, implies B is not related to A, or you can say that B is not related to A. If this is true, this condition is true, then a relation is said to be antisymmetric. We have discussed it in the previous lecture of relations. So for example, a subset relation is basically a partial order relation. How we define it? Let A be any collection of sets and define the subset relation on this as on A as follows. If we have two sets which are subsets of A is basically A is basically a collection of sets. In this collection the elements are sets. So if we have two sets U, V, which belongs to this collection, then U is subset of V for all X. If X belongs to U, then X belongs to V, the usual definition of subset. So we have to prove that this relation is a partial order relation. This relation must be reflexive, because if we take any element U, any set must be the subset of itself. So this is true. Therefore U is related to we have to prove first that this relation is reflexive. As we know that any set is subset of itself, as U is subset of U, it means U is related to U for all U belongs to A. This is true for every set. Therefore this relation is basically reflexive. Now we have to prove that this relation is symmetric. To prove that this relation is antisymmetric, if U is subset of V, then it doesn't imply that V is subset of U. This is not generally true. Therefore if U is related to V, this doesn't imply V is related to U. So this relation is not symmetric, means that this relation is antisymmetric. If this relation is antisymmetric, and there is only one condition which we have to prove, that this relation is transitive. So if U is subset of V and V is subset of W, then this obviously hold that U is subset of W by the properties which we have studied in sets. So this relation is transitive. So this relation is reflexive, this relation is antisymmetric, this relation is transitive. Therefore this relation is a partial order relation. The less than or equal to relation, this relation is also a partial order relation. You can prove it easily. Less than, every integer is less than or equal to itself. If an integer is less than or equal to y, x is less than or equal to y, then y is less or equal to x, then x is equal to y. Now we are going to study the partial order relations. So in the equivalence relation, and relation R is said to be equivalence relation if it is reflexive, symmetric and transitive. In partial order relation, any relation R is said to be partial order relation if it is reflexive, antisymmetric and transitive. What is antisymmetric? We have studied in the previous lectures. what is antisymmetric. A relation R is said to be antisymmetric if A is related to B and B is related to A. This implies A is equal to B. So this is what the definition of antisymmetric relation we have studied in the lecture of relations. Now, any relation which is reflexive, antisymmetric and transitive, that is said to be partial order relation. For example, the subset relation is basically a partial order relation. We can prove it that this relation is reflexive, antisymmetric and transitive. For example, all sets, basically any set U is a subset of itself. This is true. So U is related to U for all U belongs to A. This means that this R is reflexive. Now for symmetric property, antisymmetric property, if U is subset of V and V is subset of U, then the properties of sets U must be equal to V. U must be equal to V. This is what the property of antisymmetric. So this subset relation is antisymmetric. We can prove also this relation is transitive. For that, if U is subset of V and V is subset of U, then obviously by the properties, V is subset of W, then obviously then we have to prove U is subset of W. If U is subset of V, V is subset of W, then by the properties of transitive properties of sets, obviously U is subset of W. Therefore this relation is transitive relation, and we can say that this relation is reflexive, antisymmetric and transitive. Therefore this relation of subset is a partial order relation. We take another example of partial order relation, which is a less than or equal to relation. Less than or equal to relation is not an equivalence relation. Now we are going to prove that it is a partial order relation. So less than or equal to relation is reflexive. Obviously every number is basically less than or equal to itself. Means that either this is less than or equal to this. So this holds. Therefore this relation is reflexive. Now the antisymmetric. If x is less than or equal to y and y is less than or equal to x, so this is only possible when we say that 2 is less or equal to 2 and 2 is less or equal to 2. What does it mean? 2 is equal to 2. 2 is equal to this. 2 is equal to 2. So we can say that this relation is antisymmetric. Similarly, we can prove that this relation is transitive, because if x is less than y, y is less or equal to z, then obviously x is less or equal to z. This is true for all real numbers. Therefore this relation is reflexive, antisymmetric, transitive. So this is partial order relation. How we construct the Hayes diagrams? Let basically these diagrams we construct for the partial order relations. Let A be any set 1, 2, 3, 9, 18 and consider the divider relation on A. Now divides relation, we know that it is or we can prove that this divides relation is a partial order relation. And how we define this relation? This is basically for all AB belongs to A divides B if and only if B is equal to K for some. So this is how we define this relation, A divides B. How now we have to write the directed graph of this relation. We have to construct the directed graph of this relation. Usually we write the elements of A. We begin by writing the smallest element below, then 2, 3, 9 and 18, and then according to partial order relation, basically this relation is reflexive, so we must construct a loop at each element as we have constructed loops here. Now 1 is related to 2 because 1 divides every integer, therefore there is a arrow from 1 to all integers. Now 2 doesn't divide 1, therefore there is not an arrow from 2 to 1. Similarly 3 doesn't divide 1, 9 doesn't divide 1, 18 doesn't divide 1. Now 2 divides 18 only, so there is an arrow from 2 to 18 only. Now 3 divides 3 divides 9, and 3 divides 16. There is an arrow from here to here. Now 9 divides 18 also. So this is basically the directed graph of the relation which we have defined this on the set A, because the relation R basically, which is the relation on here, that contains the elements which are 1 1, 2 2, 3 3, and 9 9, 18 18, and then 1 2, 1 3, 1 9, 1 18. You can calculate this, and 2 divides 18, 3 divides 9, 3 divides 18, and 9 divides 18. So this is the relation. This we can write this relation, and then we can construct the directed graph, as we have already discussed how to construct the directed graph. Now how to construct the Hayes diagrams. There are 3 steps involved to construct the Hayes diagrams. First of all, remove the loops of all the vertices. We remove the loops. Here we write again these numbers 1 2 3 4 1 2 3 9 18, and we remove the loops. Then the next step is remove all arrows whose existence is implied by the transitive property. Basically you remove all arrows which shows the transitive property. Basically if 1 is related to 2 and 2 is related to 18, now 1 is related to 18, this arrow basically shows the transitive property, so therefore remove it. Next is 1 is related to 3, 3 is related to 18, so this again arrow, this shows the transitivity, so we remove it. Next is 3 is related to 9, 9 is related to 18, and 3 is related to 18, this arrow also shows the transitivity. Now 1 is related to 3, 3 is related to 9, and this arrow shows the transitivity, so we remove also this. No other arrow shows the transitive relation of this set, so therefore we remove this arrow, and this arrow, and we remove the loops. We get this. And the third step is the direction indicators on the arrows. Remove all also. Eliminate the direction indicators. Direction indicators means if you have an arrow this is basically the direction indicator, so remove also this. So what we are left, this is basically the Hayes diagram. So this is how we can construct the Hayes diagram, which shows the partial order relation. Now to construct from a Hayes diagram a directed graph, this is basically a directed graph. This is basically the directed graph, and this is Hayes diagram. Now we have discussed the steps which are involved to convert a directed graph to a Hayes diagram. Now how to convert a Hayes diagram to a directed graph? First of all, basically reverse this process. How to reverse? Mark the direction indicators this for the relations which are related, because this and construct the loops at each element, this, 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 and then construct or draw the arrows which shows the transitivity. So one is related to 2, one is related to 3, sorry, 1 is related to 2, 2 is related to 18, so 1 must be related to 18. Similarly, 1 is related to 3, 3 is related to 9, so 1 must be related to 9. Now 3 is related to 9, 9 is related to 18, so 3 must be related to this. So we have only 3 arrows which we have added. Therefore we can construct a directed graph. From a directed graph to we can construct a Hissy diagram, and from Hissy diagram we can construct a directed graph. So this is what basically we do in partial order relations. So for today it's I think enough, and we have finished with the relations. Today we have discussed the equivalence classes and some properties of equivalence classes. We have discussed also the equivalence classes of congruence modulo 3 and congruence modulo n. We have studied bit of modular arithmetic, and we have also discussed partial order relations and how to construct a Hissy diagram from directed graphs and directed graphs from the Hissy diagram. In the next lecture we shall start inshallah the functions. Till that, Allah Hafiz.